Hello everyone, and welcome back to another example video. In this example video, we'll be determining the second order, or P delta effects, in the single-story frame using the simplified stability analysis method prescribed in CSA S16-19. It should be stated that this method entails two first-order analysis, one for gravity loads and a second one for translational loads, and both of these analyses will be conducted in the structural analysis program S-frame. Now I'm telling you guys this because in this particular video I will not be showing the S-frame analysis. However, I will leave a link in the description down below for a video showing you how to conduct the required first order analysis in S-frame for this particular example. I'll also leave a link down below for the PDF notes of this example, as I know many people always request it. Now the last thing before we begin is that I hope you all are doing well and having fun in structural engineering. With that being said, let's jump into the example. Alrighty, so looking at this example, it says determine the design bending moment and axial load of member AB in the following single-story structure using the simplified stability analysis method prescribed in CSA S16. So if we look at this, it's a pretty standard steel frame. We have 3 bays, and it should be noted that only that very left-hand bay is a moment-resisting frame. If we look at the 2 beams on the right-hand side, we can see that we have hinges there which release the moment. So what would tend to happen is once we apply that lateral load HF, our frame will have a tendency to sway, and then this sway is going to be counteracted by the stiffness of that moment resisting frame. Now we know that once the frame does start to translate laterally, this applied load at the top, that WF, it's going to start creating those second order moments. Now typically as an engineering designer, what we would need to do is conduct a P delta analysis. The problem is not everyone is qualified to do a P delta analysis, and the structural software you're using may not have it included. But don't worry, CSA has your back where it has the simplified stability analysis method, where basically we can take first order analysis, which is what we're going to do, and we can determine the second order or P delta effects based on the first order analysis. So if we look at our frame, we're good to go because we have all the geometry, we have the dimensions, and we have the loading. And for this particular case, we are going to have 2 loads. We have a factored load of WF acting at 50 kilonewtons per meter over the top of our frame, and then we have an applied lateral load of 30 kilonewtons acting at the very right-hand side of the frame. For our steel frame itself, we have 3 different sections. Our beams are going to be W460 by 97, so all 3 of them. Column AB is going to be a W310 by 179. I'm going to show why that's important later, specifically in the S-frame analysis. Typically all the columns would be the same. I picked a very dense column to show you guys sway effects, so that's why. And all the other columns are going to be W310s by 97s. All right, so now that we have everything, we can actually jump into the example. So the first thing that we have to do, no matter if we are doing a P delta analysis or this simplified procedure, is we have to calculate something called the notional load. So as we talked about in the theory, S16 requires us to not only have our applied lateral load, but apply a second lateral load called the notional load, and this load basically accounts for any uncertainty in our structure, partial yielding of some of the members, stuff like that. The problem is although everything looks perfect on paper, once you give the designs to the contractor, well, chances are there might be a little bit of a mishap in the actual construction of the project, and your column or something may be angled, something like that. So this is what that notional load accounts for, is all that uncertainty. Now the notional load is actually very simple to calculate, where it's 0.005 times the total load on our story. So if we look here, our only load on our story is going to be that distributed load. So the total load is going to be WF times L, where we know that WF is the 15 kilonewtons per meter, and we know that this acts over a length of 8 plus 8 plus 8 meters. So all I have to do is substitute that into the equation. We get the following. And if I do the math, I get that this is actually equal to 6 kilonewtons. Now what we have to do with that 6 kilonewtons is we have to add that to our applied lateral load in the direction that is most detrimental. Since that 30 kilonewtons is acting left, we would add the 6 kilonewtons in the leftward direction. So again, the 6 kilonewtons that we just added, this is our notional load. Now from here, CSA basically gives us 2 different options. We can either perform a second order analysis using the complete loading of this frame, But like I said, some of us don't know how to do a second order analysis. So CSA gives us the second option, which allows us to perform a first order analysis, and then we account for the second order effects using a U2 factor. This U2 factor is basically going to take all of our moments and it's going to amplify them in our system to account for those second order effects. So as you can tell by the title of this example, we are going to go with option B. So as I mentioned, we basically have two analyses to consider. The first one is going to be a gravity load analysis. Now the important thing here, and I highlighted in red, is that we are going to analyze our frame under solely the factored gravity load. This means that we must remove all lateral loads. So if we look at our frame right here, we can see that we actually have the same frame, but I removed all of these lateral loads. Now we actually have to do a couple funny things. The first one is to prevent any sway effects, we must add a lateral roller to the story. This is why I picked a pretty beefy column for column AB or member AB. If you guys go to the S-frame analysis, what you'll see is under these gravity loads, so solely gravity loads, the frame will actually have a tendency to sway to the left because of the additional stiffness of column AB. We don't want that in our gravity analysis. We want our frame to stay perfectly vertical. We don't want it swaying left or right. So what we do is we add a roller to the end of the story. Now this is going to be important because this roller force RF, we are actually going to need it for our second analysis. So the whole goal here of this analysis is to actually capture two different things. The first one is the gravity moments and axial load. So we're going to call this MFG, which is our moments under this gravity load, and PFG, which is our axial loads under this gravity load. As we're going to see, to determine the total design moment, we are actually going to need these two factors. The second one, which is very specific for gravity loads, is we need to figure out how much reaction force is actually going to develop inside of this frame. When we do our second analysis, which is a translational analysis, we are going to actually have to take this reaction force that develops here, and we are actually going to have to add it to our lateral loads in the next analysis. So as I mentioned, I would have taken this frame and I would have conducted a first order analysis in S-frame. Now S-frame is very nice because it'll tell me everything I need to know. The first thing that S-frame told me is that under these loads, the reaction force that will develop is 11.9 kilonewtons. So again, that's going to be very important to us. The other thing that's important, of course, is the moments and axial load. Remember AB, that's what the question wanted. So what I can do is I can make a little sketch of member AB, and directly from S-frame, it'll tell us things like the axial load. So S-frame told me that the axial load in this case is negative 408.9 kilonewtons. So of course that's going to be in compression. In addition, S-frame also showed me the moment profile, which is linear at the bottom, starting from 0 and going up to negative 191.9 kilonewton meters. The most important thing, tip, trick, whatever you want to call it, I can give you for these examples, is always pay very close attention to the signs. So notice here that our axial load is in compression and our moment is negative. The key thing also to keep in mind is these loads that we just wrote down, these are MFG as well as PFG. Now, if we look at the actual design equations in CSA, we need two different moments and two different axial loads. We need one under gravity, but we also need a second one under translation. So this would lead us to our second analysis under translational loads. So just like before in gravity loads, we need to isolate the frame from all the loading and only apply very specific loads. In the gravity load analysis, we only applied gravity loads. In this particular case, we are only going to apply translational loads. So again, we removed all the gravity loads. So we have our frame here, it's looking good, and we need to apply a lateral load to this frame. Now here is where the second trick of these kind of examples comes into play. The load we apply, which I call the total translational load, is actually going to be the summation of three different things. All right, it's going to be three different things. Most students only apply one of them. The first one is the factored applied load, HF, which we got right from the beginning of the question. The second one is the notional load, which we calculated on the second slide. We found it as 6 kilonewtons. And then the third one, which almost every student forgets, so please don't forget it, is going to be that sway reaction force that we found in our gravity load analysis. So at the end of the day, we are going to have our total translational load as three different things. Again, the first one here is the factored applied load. This came right from the beginning of the question. I believe it was 30 kilonewtons. We have our notional load, which we calculated as 6 kilonewtons. And then we have our reaction force from the previous slide under the gravity load analysis, which we found was 11.9 kilonewtons. Please do not forget this last one, the 11.9 kilonewtons. If I ever see a student have an error in this type of assignment, it's usually this right here. They forget to add that sway force. So if I were to add all three of those together, I get my total translational load to be 47.9 kilonewtons. So what I do is I take this load and I now apply it to our frame. So this is the analysis we are going to conduct. Remember, there is no gravity loads in this case. It is purely just a lateral load analysis. And even though it's shown here, I also want to emphasize there is no lateral roller that we had in the gravity analysis. We want our frame to sway in this case. We will actually want to determine how much our frame is going to sway. So of course, we are not going to restrict it from moving laterally like in the previous analysis. So the goal here is actually two things, just like before. The first one, we want the moment and axial load due to this translational effect. And then the second one is actually going to be the maximum story deflection. So this is going to be a key one here. Once you see we start calculating that U2 or that amplification factor, this story deflection is actually going to play a big role. So if we conduct this analysis in S-frame and look at the deflected shape, we are going to get something like this. Now the nice thing in S-frame, of course, is it's going to tell us how much each one of these joints deflects. So what I need to do is I need to look at each one of these deflections, and the maximum deflection, well, that is going to be my story deflection, which I'm going to use in my calculations. So I see I have 41.7, 41.7, 41.9, and at the very end I have 42 millimeters. This, of course, being the largest. So what I would do is I would select this one, and I would say that this is going to be my story deflection, delta F. Again, we are going to use this a lot when we start doing our U2 calculations. But remember, that's only just one of the goals. Another thing we have to write down, of course, is going to be the moment and axial load under this translational analysis. So I'm going to draw a little picture of my member, and from the analysis, I find that the axial load is 35.9 kilonewtons. So again, sign convention matters here a lot. Remember, in our last analysis for gravity, we had it as negative or in compression, which makes sense under gravity loads. Under these translational loads, this member, AB, actually turns into tension. So this is why you really want to make sure that your sign conventions are up to date, because if I had this in compression thinking, it's a column, chances are it's in compression, well, I shoot myself in the foot a little bit, because this tension is actually going to decrease the loads in our column, which is a good thing as designers. We want to try and have the smallest loads possible, because then we have a cheaper design. As you guys have probably picked up by now, it's all about money in structural engineering. So the cheaper the design, the better off you are. But remember, axial load is just one of the two things. We also need bending moment. So directly from S-frame, we can find the bending moment profile, which starts at 0 and goes linearly up to 164.6 kilonewton meters. Again, note sign convention. In the gravity load analysis, it was linear as well, but it went into the negative moment region. In this case, we have positive moments. So as we are going to see, everything is going to start counteracting each other. But this is it for the first order analysis. So from here, we just obtained MFT as well as PFT. From here, along with our gravity load analysis, we actually have everything we need to start calculating that amplification factor U2. So if we look here, the first thing that we are going to have to do is calculate something called PSE. When we calculate this amplification factor, U2, there's going to be two major calculations, PSE and U2 itself. So we're going to start off with PSE, and as we can see, it's a pretty gross formula. It has a lot of different components, but as we can see, a lot of them are just common sense and come directly from the frame itself. Notice here too that I have column AB and CD listed as green, because they are a part of our moment resisting frame. That's going to be important a little bit later on. So let's go through some of the easy parameters. If we look at this parameter right here, this is simply just going to be the story height. If we look at our frame that we were given, we can see that it is 6 meters, so HS in this case is going to be 6,000 millimeters. Now notice how I have it in millimeters. That's going to be something a little bit special later on. And if we look at the formula for PSE, notice that we take our story height and divide it by our deflection. Our deflection is usually in millimeters, so therefore I want my story height also in millimeters. If you have your deflection in meters, then you can leave your story height in meters. It's just to make sure that you keep consistent sign convention. The second thing that we have in our formula that's easy is this delta F, or this story deflection. Well, from the previous slide, we found it as 42 millimeters. Nice and simple. Remember, this came directly from a first order analysis. So although you're avoiding a second order analysis, always keep in mind that you are still going to have to do a first order analysis, which isn't fun, but it is what it is. The next parameter, again, is pretty simple. We have PSF, which is the total vertical load supported by each story. If we look here, we only have one story, which is nice, and the total vertical load is that 50 kilonewtons per meter. Now, PSF is going to have units of kilonewtons. It's an axial load, or a concentrated load if you want to think of it like that. So what we need to do is we need to take that 50 kilonewtons per meter and convert it into a single load. How do we do that? Well, we multiply it by the distance which it acts. So we have 8 meters plus 8 meters plus 8 meters. So PSF is going to be equal to W times L. So we take the 50, we multiply it by 8 plus 8 plus 8, and we get 1200 kilonewtons. Nice and simple. So those are the easy parameters. There's two left, and this is where it gets a little bit more challenging for students. The first one is the total vertical load carried by the moment resisting frame. So this is exactly why I highlighted those two moment resisting frames. If we were to look at our structure right here, it's pretty simple because the vertical load is solely going to be that distributed load. So we know it's going to be W times the length. But here's where the trick comes in. The length is going to be only the tributary area associated with those moment resisting frames. So if we were to look at our two moment resisting frames, they only pick up the load that I've highlighted here. They pick up the complete load of that first beam between D and B, but then that second column, AB, it only carries half of the load of that middle beam based on tributary area. So if we were to do this calculation, we are still going to have 50 kilonewtons per meter, but the distance is actually going to be 4 meters plus 8 meters. Again, this is based on tributary area. I do that calculation and I get 600 kilonewtons. So I said that this was a little bit harder, but let's be honest, you are all very smart people. You guys are laughing, saying, Clayton, you know what? Get to the actual hard stuff. This is still baby stuff. Well, if we look at our formula above, we're actually doing really good because we only have one parameter left, which is VSF. Now, VSF is the total factor shear on the story. Now, here's the nice thing. This is going to change a little bit in the next example when we cover a multi-story frame, but for a single-story structure, the total factor shear is just going to be the total lateral load that we applied to our structure. This is why I have it written down on the very right-hand side of our frame. We know that our factored shear in this case, being the total lateral load, is going to be the summation of the factored applied load, the notional load, and the reaction force, which we already calculated as 47.9 kilonewtons. So we know that VSF in this case is just going to be 47.9 kilonewtons. And this is great for us because now that we have VSF, we have every single parameter in our PSE equation. So it's everyone's favorite time, which is plug and chug time. We take our formula, we look at it and say, you know what? I know absolutely everything in here, so I can just substitute everything that we've already identified. Make sure that you keep good sign convention though. So notice how for my story height and deflection, they have the same units, as well as PSF, MF, and PSF, they both are in units of kilonewtons. You can calculate it, and in this case, I get 6,330 kilonewtons. Now this is nice because once we have PSE, we can go to the thing we actually want, which is that amplification factor U2. Now it sounds like it's going to be a pretty scary, pretty gross formula, but it's actually pretty simple. And the nice thing is if we look at these two components, PSF and PSE, we already know what they are. So this is just another plug and chug scenario. We can throw them both in and we get 1.234. Now this is actually very important because this is going to be the magnitude we amplify MFT and PFT. The key thing to keep in mind here is we're only amplifying the moment and axial load due to the translation of our frame. We're not amplifying the gravity moment and gravity axial load, just the moment and axial load related to translation. So far we're looking pretty good. We have calculated everything we need. Now we can obtain that total design moment, which was the objective of the question, by simply adding the gravity moment and axial load to the amplified translational moment and axial load. We have a nice formula for this, where MF is equal to MFG plus U2 times MFT, which is great because if we look at this formula, we know absolutely everything in there besides MF, but MF is the goal of the question, so we're actually almost done. If we look at axial load, it's the exact same formula, but rather than moment, we have axial load. And again, we know every parameter in here besides PF. But again, that's the objective of the question. So what I like to do here is I just like to take my sketches that I wrote down from S-frame and say, you know what? Under my gravity loads, this was my scenario. I had a linear moment profile going from 0 to negative 191.9, and it was under an axial load of negative 408.9 kilonewtons. Now, some of you may be saying, you know what, Clayton, where did you get that? You're just pulling this out of your butt? Well, don't worry. This came directly from slide number 3. So in case you forget where these calculations came from, they're in slide number 3. The second thing that we have was we had our bending moment and our axial load under our translational loads. So we remember from S-frame that we had an axial load of 35.9 kilonewtons, which is actually in tension. And we had a bending moment profile, which was again linear, going from 0 to 164.6 kilonewton meters. Again, you're wondering where this came from. This particular one came from slide number 4. So now that we have both of these, as well as our U2 factor, we can actually determine the design loads MF and FP, or PF. From here, I'm going to draw a sketch, and then I'm just going to go through each one by one. So if I wanted to find out the total design axial load for my structure, what I'm going to do is I'm going to take the axial load from the gravity analysis, which was negative 408.9, and I'm going to add it to the amplified axial load from the translational analysis. So from the translational analysis, it was 35.9, and I amplify it by 1.234, and I get my total design axial load to be negative 364.6 kilonewtons. Which is great because again, if we look at the gravity load, based on these loads, the axial load in this column was almost negative 411 kilonewtons. But my design axial load is almost 50 kilonewtons less than that. So in this case, the second order effects actually helped us out. We can do the same thing for moment. So if we look at A, we can see that the moment, of course, is going to be 0 because the gravity load moment was 0. The translational load moment was 0. We take 0, add it to 0, well, it's still going to be 0. But if we look at the top of our structure, we are going to take the gravity load moment and add it to the amplified translational load moment. And as we can see, since we're taking something very negative and adding it to something very positive, the moment at B is actually only going to be 11.2 kilonewton meters. And of course, it's going to have a linear profile. But if we look at this, this is actually where it starts to get a little bit crazy. Under the gravity loads, our moment was almost negative 200. Under the translational loads, our moment was just about 165. But our actual design moment is only 11.2 kilonewtons. So this is why, again, I emphasize sign convention, because if I didn't have, let's say, the gravity load as negative 191 and had it as positive, well, then my design moment would almost be 400 kilonewton meters, which is crazy. The actual design moment, as we can see, is 11.2. Now, that would be it. This is actually the simplified analysis procedure, because at this point here, we have our beam, we have our moments, and we have our axial load. We can simply design this as a beam column. So I go through my beam column checks. If it meets everything, we are actually good to go. However, some students will say, well, you know what, Clayton? This was a simplified method in CSA, and I know CSA, they like to be conservative. How conservative was this method? Am I really overestimating my design loads? Well, let's take a look. So we can also conduct a second order analysis directly to obtain the design loads, as long as we make sure we include the notional load. One common mistake I see a lot of students make if they do a direct second order analysis is they don't include the notional load. Remember, notional load accounts for uncertainty in our structure and partial yielding. So we have to include that no matter what kind of analysis we are going to make. However, if we were to compare the two, my first order and second order analysis, well, from the previous slide, we were given the following design loads, where the moment at A was 0, the moment at B was 11.2, and our axial load was around 365 kilonewtons in compression. If I were to go in S-frame, and the video example I have shows you how to do this second order p-delta analysis, well, we get the same moment profile, and if we look at the loads, well, the moment today is still going to be 0, which is great. The axial load is negative 365.3, so as we can see, the difference there was only 0.7 kilonewtons, really good. And then the moment at B was 8.4. So as we can see, there's a little bit of conservatism, but once we get into higher moments, which we'll see in the next slide, it's actually not that bad, where the difference between the two methods is usually plus or minus 5 kilonewtons per meter. It just looks bad right now because MFB using this method was already so small to begin with. Now again, one of the things that we emphasized was in this example, the moments counteracted each other. Therefore, our total design moment and axial load was very small. However, if we looked at member CD instead, and if you want to do the calculations, go for it, we would see that things start to become a little bit different. Under gravity loads, just like before, we have column CD in compression, and we have a negative moment at the top. However, when we look at the translational loads, we also have a negative moment at the top, and the column is also in compression. Remember that for member AB, both the axial load and the moment were positive. But for member CD here, they're both negative. So what happens when we look at the design loads for this particular scenario? Well, everything gets amplified even more. So if I were to look at the moment at A, as we can see, 0 plus 0, that's going to stay 0. But where things get interesting is when I start looking at axial load. Remember, I'm going to take my gravity load of 191 and add it to the amplified axial load of the translational analysis, which was negative 35.9. And in this case, I get my total axial load to be negative 235.4. So in this case, our axial load was actually amplified into a much larger value rather than the loads counteracting and resulting in a smaller value. And the same thing happens for the moment. I take my gravity moment, which was negative 120.8, I amplify it by 1.34 multiplied by negative 122.9, and I get negative 272.5 kilonewton meters. So this is again just me emphasizing, pay attention to sign convention. Some members will have their design loads lowered due to second order effects. Other members will have their design loads increased due to second order effects. The other thing that I want to mention really quick, and this is the last thing, notice that my U2 factor for member CD was the exact same for member AB. The U2 factor is going to be the same throughout the story, so you don't have to worry about that too much. It's one of those nice things. But yeah, that's it for this example. I hope I was able to clear up some of the hardest parts, I guess, of the simplified analysis method. I find that students love design, but they hate anything to do with structural analysis. So again, I hope I was able to clarify some things, and hopefully you guys realize that this method is actually pretty simple to do. It's not too bad. The only thing you may not like is the S-frame analysis, but again, I will have a video link in the example down below showing you exactly how to do that. But yeah, that's it for this video. I want to thank you guys so much for listening. I really appreciate it. I hope you all have a wonderful day, and I will see you all in the next example video.